Okay, I'm going to go through the problems from the sample exam 3. What you need to make sure you do before you watch this video is complete all of these problems on your own. Give each of them a try. Lock yourself in a room, don't peek at your notes. Give each of them a try so that you know where you stand going into the test. Alright. So, first problem, we were given f of x, f prime of x, and f double prime of x, and we were asked to complete about 10 different tasks. So each of these questions is about the function f of x. So what is the domain of f of x? Well, we only look at the denominator here. It will never be 0, so it's a rational expression. We can plug anything we want into it. So the domain is negative infinity to infinity. Next problem, state all the x and y intercepts. So if we set x equal to 0, we'll get the y-intercepts. So f of 0 is 0, just by plugging it in. And if we set y equal to 0, or f of x equal to 0, we get the x-intercepts. And once again, if we solve the equation 0 equals x over x squared plus 5, fraction equals 0 means the numerator equals 0, so x is 0. So there's only one intercept, the origin. Okay, for horizontal asymptotes, that will be a limit as x goes to plus or minus infinity. So in this case we can use L'Hopital's rule because both the numerator and denominator tend to infinity as x goes to infinity, or as x goes to minus infinity we end up with negative infinity on top, but infinity on bottom. But at any rate, since this is a rational expression, we can actually just use the coefficient test. So the degree of the denominator is greater than the degree of the numerator. So in this case, the denominator is going to grow much faster. The fraction is going to tend to 0 as x goes to infinity. So y equals 0 is our horizontal asymptote. Okay, for vertical asymptotes, we just look, the denominator here is never 0, so there are no vertical asymptotes. Okay, for intervals of increase, in that case we need to find the critical values to break up the number line. So the derivative f prime of x here, it also is defined everywhere. And if you set the fraction equal to 0, you'll find that x has to be plus or minus square root of 5, so just the numerator has to be 0 to make the fraction 0. That breaks up our number line into 3 intervals. We can plug test values like -4, 0, and +4 into f prime, and we get negative, positive, negative, which means f went from decreasing to increasing to decreasing, and that gives us the interval of increase is only this middle interval. Okay, for the local maximum values, we've already done the work for the test. We can just immediately say the local maximum value occurs at x equals square root of 5. And I asked for the x value, not the output value, which is what the maximum actually is. And for local minimum, we can read that straight from this test as well. So x equals negative root 5. Okay, for concavity, we need to break up the number line once again. We do that by setting the second derivative equal to 0. And in that case, we get 3 solutions. Negative root 15, 0, and root 15. That breaks up our number line into test intervals. And, oh no, error on my slide. I think we had a negative and a positive. I didn't go back and fix those. Okay, so slight error there, but it will be concave down, concave up, concave down, concave up. Yeah, over here the things are right. I just didn't get the signs right down bottom. So the intervals where it's concave down are from negative infinity to negative root 15, and from 0 to root 15. Okay, where are the inflection points? Well, in this case, it changed from a frown to a smile to a frown to a smile, so all 3 of those x-coordinates are the x-coordinates of inflection points. Finally, how do we sketch the curve? Well, we put all of that together. We know where it's concave down, we know where it's increasing or decreasing. In this case, the y values actually don't ever get very large. If you want to plot this on Desmos, just throw a 10 up in the numerator and you'll get a better sense for where the curves are. But yeah, what's concave down till about here, still decreasing, concave up, bottoms out, then still concave up but increasing, then concave down, maxes out here somewhere, and then still concave down but decreasing, and then finally concave up. You can't really see it very well, but if you throw a 10 up in the numerator and plot it in decimals, you'll get a better sense for it. Okay, problem number 11. For each of the functions, find the global minimum and global maximum values on the given interval. So in this one, just interval 0 to 2, nice small interval for us, a cubic equation. So to get the critical values, we differentiate. We set the derivative equal to 0, and that's going to give us two critical values. So x will either be -3 or 1. However, -3 is not in the interval from 0 to 2, so we only get one critical value in this closed interval, so we can just compare the output. If we plug in 0, 1, or 2, we don't need to worry about x equals -3, and we get three different outputs. Which one of them was largest? 4 was the largest, -3 was the least. So on the interval from 0 to 2, y had a global maximum value of 4 and a global minimum value of -3. Okay, new equation here. Oops, y equals 2 theta minus 4 sine theta, this time on the interval from 0 to pi. So we get the critical values by taking the derivative, setting the derivative equal to 0. In this case, if you set this derivative equal to 0, cosine of theta would have to be 1/2. And then once cosine of theta equals 1/2, we can identify where that happens on the unit circle. It is one of the values that we have memorized. It happens at x equals pi over 3, or theta equals pi over 3, rather. So we have two endpoints and one critical value that's between those endpoints. I mean, there were infinitely many solutions, but we only cared about the pi over 3 solution because we were restricted to the interval 0 to pi. So if we plug in 0, pi over 3, and pi, we can compare the outputs. The largest output value is 2 pi. The smallest output value works out to be 2 pi over 3 minus 2 root 3. It's a negative number. That's all we really need to note to determine that it's the least of the three values. So, on the interval 0 pi, y had a global maximum value of 2 pi and a global minimum value of 2 pi over 3 minus 2 root 3. Okay, here we have the Bessie the cow type problem, trying to create a pen here so that we maximize the area. This time we have 200 feet of fencing. So we have 3 y's and 2 x's according to the picture, and that accounts for the 200 feet of fence. We can solve for x or y here. I chose to solve for x. So x, if we subtract the 3y across, divide by 2, we get x equals 100 minus 3/2 y. We want to maximize area, which is x times y. Oh no, there are too many variables. So we replace x with what it's equal to in terms of y, and then we're ready to maximize the area. So we differentiate, find the critical values. So the derivative is just 100 minus 3y, which is definitely defined everywhere. So we set the derivative equal to 0 and find out that y equals 100 divided by 3 is our critical value. And the smallest that y can be is 0. The largest it could be, if we took all 200 feet of fence and divided it by 3 into 3 pieces, because there are 3 y's in the picture. So we could use either the first derivative test, the second derivative test, or just this closed interval test. So we can compare the outputs when we plug in 0, 200 over 3, or 100 over 3. And it turns out plugging in the critical value gives the greatest of those 3. Therefore, area is maximized at y equals 100 over 3. And then since the question asked for the dimensions of the pen, we need to figure out what x is. So when y equals 100 over 3, we substitute back in up here, and we can figure out what x equals. So it's 100 minus 3/2 of 100 over 3. crunch those numbers. That's just 100 minus 50 is 50. So the pen should have outside dimensions of 100 over 3 feet by 50 feet. The next question asks us to find the point x comma y on the line 6x plus y equals 9 that is closest to the point 9 comma negative 5. Alright, so we want to minimize the distance. I always identify what is it you're trying to minimize or maximize. In this case it's distance d. Oh no, there are too many variables. So we substitute y equals 9 minus 6x into d and crunch the numbers, and it gives us another radical here. Yeah, not the prettiest thing we've ever seen. In this case, we could just find the derivative of d and get the critical values, or we can note that to maximize d, or sorry, minimize d, we want to minimize d squared. That way we get rid of the radical, get slightly prettier numbers, although they're not pretty, not particularly pretty in this case. Alright, so when we set the derivative of d squared equal to 0, we find that x is going to be 186 over 74, or 93 over 37 if we simplify the fraction. Okay, now that we've got our critical value, we absolutely have to run a test because we want to get credit for the problem. So we can break up the number line into two test intervals, one on each side of 93 over 37. We'll plug in 0, we can plug in 10 into the derivative. One's negative, one's positive. So if it goes from decreasing to increasing, we indeed did have a minimum. So d squared is minimized at x equals 93 over 37. Thus, d is also minimized at x equals 93 over 37. So it's just a matter of finding the y value so we can name the point. Plug in x equals 93 over 37 and crunch the numbers, and we do indeed get a y coordinate, so we know the point on the curve is closest to 9 comma negative 5. So the point on this line is closest to that. Alright, up next, an electric voltage V across the resistor R generates an electric current I given by the formula V equals IR. Okay, I know absolutely nothing about electricity. It's like a magic fire that makes things happen, okay? So that's okay. We don't have to know much about electricity. We just read the problem. It told us the formula. If a constant voltage of 9 volts is put across the resistance, that's increasing at a rate of 0.2 ohms per second, then when the resistance is 0.5 ohms, at what rate is the current changing? Okay? My eyes just glaze over. I really do know nothing about electricity when I read that. But it's not a problem. R was for resistance, so we saw that resistance was increasing at 0.2 ohms per second, so dr over dt is 0.2 ohms per second when R equals 0.5 ohms. And it said the constant voltage, so that means V is not changing. dV over dt is 0 volts per second. And then the problem says, at what rate is the current changing? The current was I, so we want di over dt when the voltage equals 9 volts. And notice, since V equals 9 volts, and the resistance is 0.5 ohms, in that case we could solve for I here. Because V equals IR, just plug in 9 for V and 0.5 for R, and that gives I equals 18. So I was, okay, the units aren't even obvious. We know that V is volts, R is ohms, so I has to be volts divided by ohms. We differentiate our formula here. Looks like we need to use a product rule. So dV over dt equals derivative of the first times the second plus the first times the derivative of the second. And then we just plug in the pieces from the problem. So 0 equals di over dt times 0.5 plus 18 times 0.2. And then it's just a matter of solving for di over dt. And when we do, we get negative 36 over 5. And here I just state that we can get the units of I by just doing volts divided by ohms. And apparently that's what an amp is, volts divided by ohms. I had no idea, but I wrote it down, figured it out for the slide. If a constant voltage of 9 volts is put across a resistance that's increasing at a rate of 0.2 ohms per second when the resistance is 0.5 ohms, then the current is decreasing at a rate of 36 over 5 volts over ohms per second. I don't have to understand what the units mean. The units are given to me, and I can work with it from there. Alright, in this problem, a hot air balloon is rising vertically, tracked by an observer 5 miles from the liftoff point. At a certain moment, the angle between the observer's line of sight and the horizon is pi over 3, and it's changing at a rate of 0.1 radians per minute. How fast is the balloon rising at this moment? So I've drawn the picture this way. At the moment we care about, when the angle is pi over 3, the balloon's going to be much higher. So you can, and if it's increasing at 0.1 radians per minute, that's still going to be growing awfully fast. So that balloon's going to be booking it. So from this picture, to relate the variables, you see a theta and y there, opposite and adjacent sides, we're going to use the tangent function. Tangent of theta is y over 5, or just get rid of the fraction by multiplying both sides by 5. Y equals 5 tangent theta. Okay, we need a statement of what we know and a statement of what we want. We know that the angle is changing, or I should say increasing at a rate of 0.1 radians per minute. And we want to know how fast the balloon is rising, so we want to know how quickly y is changing. So we want dy over dt when theta equals pi over 3 radians. Okay, so we just differentiate and go from there. So the derivative of 5 tangent theta is 5 secant squared theta, d theta over dt equals dy over dt. And we can plug in the pieces. When theta equals pi over 3, we're going to get 5 secant squared of pi over 3 times 0.1 equals dy over dt. Just a matter of crunching the numbers. Secant of pi over 3 is the reciprocal of cosine of pi over 3. So you're going to get 5 times the square of 2 times 0.1. So 5 times 4 times 0.1 is 20 times 0.1 is 2. 2 miles per minute. So when the angle between the observer's line of sight and the horizon is pi over 3 radians, the balloon is rising at a rate of 2 miles per minute. It's like 120 miles per hour. This balloon is booking it.